I don't think that was the agreement. I'll talk through this bit if you want.
I can't see this. I've got the chat in the way. I can't really see the screen properly.
Come
Right.
on, sort yourselves
That's
out.
no problem. I'll go first, Mike, if you want.
Go on, Connor,
No,
read
that's
it
right.
through.
I want the bipolar transistor first, please.
Do you want me to read it, or can you all see it?
I want you to explain to all of us what the transistor is and what its action is in a circuit.
Well, okay. So I just looked at what it actually is, essentially. So, bipolar transistor, BJT for short, is a versatile discrete semiconductor device. They're designed primarily to perform one function as a single semiconductor, as opposed to having to build multiple semiconductor components into a circuit, essentially. And then, sort of skip over Macaulay, and Macaulay knows more about that. He looked into how it is as a switch.
Yeah.
Yeah. Yeah. Come on, Macaulay, you dosser.
Come on, less of the abuse, thanks, Dom.
Me, I can't see the
Fuck
screen
up.
properly. I've got this
Oh,
chat
that
thing in the way.
You can
Put it out of
minimise
the way then.
You can minimise the chat.
I can't. There's something going on.
Yeah,
Come
you
on,
can.
idiot.
It's at the top.
I don't know. It's not working.
Oh,
Come
yeah.
on.
You'll have to read it for me, Connor. I can't see.
I think you can get this bit off.
Just read what I put.
All right, Macaulay states a BJT can be used as an amplifier, filter, rectifier, oscillator, or even a switch, which we cover an example in the first section.
Did you?
The transistor will operate as an amplifier or other linear circuit if the transistor is biased into the linear region. The transistor can be used as a switch if biased in the saturation and cutoff regions. This allows current to flow or not in other parts of the circuit. It's like an electrical check valve for all the hydraulic people out there.
Oh, big up hydraulic people.
Yeah.
Big ups. Better than electronics.
And he's got a diagram there.
God, those might be people on Tinder.
Just before we move off that, I'm going to say, if you take this middle circuit here, yeah, the idea is that this could be a higher power, high current device that you can switch with a small signal here. Who done that?
Who's drawing on my fucking thing?
Who did it?
Who done the circles?
Don't know. Can I find out?
I don't know.
Proceed.
Right. What the idea here is, as a transistor as a switch, is we could have a small signal on the here, let's say, I don't know, like half a volt, millivolts, and use that transistor to turn on a much higher current that will flow through this lamp from this battery here. So using low voltage signals to switch higher voltage signals as a use of a transistor as a switch. Also, they can switch much faster than a relay. Yeah. So if you think of a mechanical relay that you'd probably experienced at work, where you've got a coil and you use that to switch motors and things off and on,
Yeah.
If you use a transistorized output as a switch, you're talking very much quicker response times. The other thing is you haven't got that mechanical wear that you've got in a relay, because a solid state is not going to wear up mechanically. Okay, and if to see you've got two different types, NPN. So we're looking at that as N, N, P, N. This is a sandwich of three regions, N, P, N, or P, N, P. So where the arrows go, and the arrow's always in the direction from P to N. So that base must be P-type material, and you've got two N-type materials. With the PNP transistor, the arrow's going inwards. It's going from N here, going from P here, sorry, to N in the middle, to P at the outside. If you look at the battery connection, that's the other way round. So you choose whether you go NPN or PNP according to application. And we'll talk about that a little bit more when we look at how you set one of these up in a real circuit. Okay?
Yeah.
When you're asked for basic information, be careful about writing something that you might not understand. Operating in the linear region. Can either of you tell me what that means?
Macaulay added that section, so Macaulay.
Probably, or what I'm saying is probably not. So that's what you have to be a little bit careful of. Yeah.
Yeah.
If you just unshare that for me for a minute.
Wait 1 minute.
Yeah.
So rich.
I'm just gonna share something else. My screen and go back to our document. Right. I think I can add a page. Yeah, that was me. The other thing is we can set this transistor up. PNP type, like so. Where here is the input. We put a small signal on the input, and we control the current going in here. Small current going in here will allow a much larger current to flow between the collector and emitter, and so our output signal is amplified. So you put a small sine wave input, you get a much amplified sine wave output, and we'll have a look at that as well, more detail in a later session. So they can be used as a switch, yeah, and they can combine several of them together to make banks of switches and so on, and eventually you get to your microprocessor that we know and love, that all our computers have got inside them these days. Okay, but also this would be called a common emitter amplifier, because the emitter is common to both the input and the output. All right, there are circuits that also use common collector and common base formations to do other slightly different things. All right.
Yeah.
So, Dom, are you ready to tell us about you and your gang?
I'm ready.
Ready to tell us about Mosfets and JFETs?
Oh yeah. All right. Oh, that's me. All right. Can we see the whole? There we go. All right. So a Mosfet is probably the most common type of FET. Mosfet stands for metal oxide semiconductor field effect transistor, which is a mouthful. Yes. It utilizes an insulator, which is typically whatever that is, maybe like silicon oxygen.
Silicon dioxide.
That's the one. Between the gate and the body. It's used for switching and amplifying electronic signals in the electronic devices. It is a 3-terminal device with a source, gain, and drain, which is displayed in this beautiful diagram below. By applying the voltage at the gate, it generates an electrical field to control the current flow through the channel between drain and source. There is no current flow from the gate into the Mosfet. There you go, that's all I got.
Yeah, okay. Now, what about the JFET?
Oh, that's not mine, I didn't do that.
Jake?
Yeah.
Logan? What you got
What you want to know? What you want to know?
I want to know how a JFET works. Very similar, but I want to know. And so do your colleagues, Jake and Logan.
JFETs are exclusively voltage controlled, so that they do
You
not.
got a picture for us, Jake, or not?
Yeah, I have.
Yeah, can you share it?
I can try.
Okay, thanks.
Me to share one for you.
Is it just share
If
screen?
you got something, Logan. Yeah, if you share your screen, you can pick whatever you want to share.
Logan, that's Jake talking.
That was Logan a minute ago, wasn't it? I thought.
That is me.
Jake.
There you go, there's sound.
There we go.
Oh, where's it gone?
You're both sharing the screen.
Oh.
What are we? Should I turn mine
Go
on?
on, unshare, please.
I was just trying to help. I can't. Where is it?
What is
I've got
going
my
on?
document up now.
Hey.
Ah, here we go.
Who's this?
That's
That's
mine.
Jake, isn't it?
So JFETs are exclusively voltage controlled, so that they do not need a forward or reverse bias current. Electric charge throws through the semiconducting channel between the source and the drain terminals. They can be used as electrically controlled switches, amplifiers, or voltage controlled resistors. When there is no voltage across the gate and the source, the channel becomes a smooth path which is wide open for the electrons to flow. But the reverse bias happens when the voltage is applied between a gate and the source is reverse polarity. That makes the P to N junction reverse, makes the channel narrower by increasing the depletion zone to put JFET in cut-off or pinch-off region.
Yeah. Okay, just hang on a minute. Let me just turn that off. And so, just to help with that a little bit, just can you put that back on, Jake,
Oh yeah.
please?
Is it on?
No, I can't see it at the moment.
It says that I'm sharing.
You are.
Here we go. I got it. Right. It's gone again now. Ah, here we go. I'm trying to write on it, but I can't. Okay, take off, Jake. I'll put my page on and do it separately on the page on the whiteboard. right?
Yeah.
What the hell?
Right. So let me try and remember your diagram, Jake. There's a two p-type regions. And then this is n-type material. Yeah.
Yeah.
There's a gate. Drain.
That goes all the way around it.
Source. Yeah. And when there's no voltage, 0 volts on the gate, current is free to flow. From there to there. So current's free to flow through from source to drain. Yeah.
Perfect.
When you apply a voltage to the gate, yeah, this channel starts to close. And so less current can flow. And indeed, after that, when it gets to a certain level, they'll nip right up and new current will flow. So it's like a valve, really. As you vary the gate voltage, you open and close the channel, allowing more or less current to flow. Yeah. Okay with that?
Yeah.
All right. So and the Mosfet that you done was similar, Dom, except you got that the metal oxide substrate in there between the gates. There's no actual current flow from the gate. It's still an opening and closing of the channel. Yeah. So you either got an open channel or a closed channel, and they can switch very, very quickly and quite high currents if you get the dependent upon type, of course. And again, we'll look in a bit more detail at how they work and what their uses are a bit later on in the module. Yeah. Okay. Yeah. Everyone all right with that?
Yeah.
Yep.
Right. So last but not least, we're moving on to Nathan and Taylor, who are going to tell us about operational amplifiers.
Nathan and Taylor.
You want to go
What
first,
a
Taylor, or
team
do you want
that
me to go
is.
first? I'm going to be completely honest with you, Mike. I was working with Regan because you told me I was with Regan, not with Nathan. But I got some information.
Yeah, well, Regan's been a bit of a fly in the ointment because he's disappeared, isn't he? So
yeah,
a bit muddled, but someone's got to tell us all about.
What's Dom doing? Being drunk?
Who's going to tell us a little bit about operational amplifiers then?
whoever wants to go first.
Well, I can, but I'm on my phone, so I can show you my laptop screen, but I won't be able to share it.
Okay, well, do your best.
Can you turn the camera on there or not? Oh, yeah. I don't know if you can see that very well. Or is it all?
Not really, no.
That looked blurry to me.
I can't see it.
I can read it out to you anyway.
Yeah,
Shall I just read it out?
Yeah, and I'll do some from what I'll build on what you say, Nathan.
Operational amplifier, commonly known as an op amp. This allows for a signal to enter the input terminals, which the voltage will have a gain and become larger at the output terminal. Essentially, this uses gain to increase signal voltage used for feedback circuits. No current is passed through an op amp. The voltages on the output can't go above or below its power supply voltage, to which it saturates and levels off as it reaches the minimum or maximum. And I just did add like a diagram of an operational amplifier, but obviously you can't see it.
Yeah. All right. Well, I'll help with that. No worries. You've obviously done so. You've got the basics there. All right. If you'd like to, I'll just put this back on.
I don't know if Taylor's got more information than what I have. So.
Yeah.
Have you got anything, Taylor?
I found a little bit on that they use the actual operation amplifiers are used in mathematical operations of an input voltage. I can what Nathan said is basically what I had, a lot to do with a high gain and high input independence as well.
Yeah. High input impedance. Impedance. Yeah.
Right. I thought it said independence, but yeah.
Okay. Yeah. I'll explain that a little bit more. All right.
All right. Thanks.
Let me share my screen again. Right, operational amplifier. Op amp for short. They got a symbol like this. Yeah. They got a positive and a negative input. Yeah.
Yeah.
And then they always have shown. You didn't always put them on, but they'll have a plus 12, minus 12, or plus 15, minus 15, or some positive and negative power supply. Okay. And that's the limits at the output. So it'll saturate just before 15 volts positive, 15 volts negative. All right. But for a very small input here, you can gain a lot at the output. Yeah. Because what's open is a differential amplifier. It amplifies the difference between these two terminals. So you might have microvolts on the input and have plus 15, minus 15 voltage at the output. Yeah, because the open circuit gain typically greater than 1 million. Yeah. So that's saying if we put 1 microvolt in at the differential input, we'll end up with 1 volt out at the output. But with further circuitry, you can control that gain and set that gain to what you want. So you can make it a gain of 10, a gain of 15, a gain of 100, using further circuitry, and we'll look at that more. Also, you can use it to add voltage inputs. So you can make it an adder, quite often used in instrumentation to take very small signals from sensors and turn them into something a bit more useful. And the input impedance, looking in here, Z in is very high. That means it doesn't draw very much current from the device that's connected to its input. So microamps, yeah, and it has a low output impedance, so it transfers well to the circuit it's transferring into. All right. So at that
Alright.
level, its action, that's what you need to know, that it amplifies the difference between these two terminals, marked plus and not minus. It has a very high, what's called open loop gain of million or more, which we can bring under control using some other basic components, so that we can set what the gain is to anything we want it to be. Has a high input impedance, so that it doesn't draw lots of current from the device that feeds it. And it has a low output impedance, so that it easily transfers all the output power to the next device down the line. All right. And on most circuits, these two terminals will be left off, but you mustn't forget to connect them to plus or minus 15 volts. All right.
Yeah.
Everyone reasonably okay with that? Yep.
Reasonably, yeah.
Okay. So what we're going to do now is just finish up with having a look at how we can analyze the action of a junction diode using the circuit simulator. All right, I'm going to do this with you now, and then maybe give you a real diode device to have a look at that's slightly different to this one. All right, so we're going to analyze the forward and reverse current characteristics of this simple diode. It's not any particular diode, it is one in the non-linear components section on GUCS. For the benefit of the exercise, we shall assume it has a maximum forward current of 500 milliamps. So what we need to do is make sure that we don't get any more than 500 milliamps flowing through the diode.
I'm back.
Okay. Now, if we're going to have this the input voltage up to 3 volts, yeah, how can we find out a value of resistor here that will only allow 500 millivolts to pass through the diode? Bearing in mind that we know we're going to get 0.7 volts across the diode. If there's 0.7 volts across the diode, how much are we going to experience across the resistor? What does Kirchhoff's law say? Silence. Come on, boys, you can do this. This voltage here is 3 volts.
In any closed loop network, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop.
Yeah. So VS, the supply voltage, is equal to VR plus V diode. Yeah. Therefore, VR is equal to VS minus V diode, which is 3 minus 0.7 equals 2.3 volts. So if we've got 2.3 volts across there, how can we find out what size resistor to use if we want the maximum current to be 500 milliamps or half an amp?
Sorry, what was the question?
Well, we've got to find out a value for this resistor R1 here.
Yeah.
We've got 2.3 volts across it. We're going to have when the diode is conducting at its maximum. 0.7 here, 2.3 volts there. We're going to have 500 milliamps flowing through it. So how do we find out the value of that resistor? What's the formula for R?
Can you just do Ohm's law?
Yeah. That's VR over I, 2.3 over 0.5 equals
4. Something, I don't know, we can't do it. 2.3 divided by 0.5 is 4.6.
4.6 ohms. Yeah?
Yeah.
So we want a resistor of at least 4.6 ohms in series with that diode to make sure that at 3 volts we don't get any more than half an amp flowing. Yeah?
Yeah.
So what we need to do is resistors come in what's called preferred values. And the sort of de facto standard these days are resistors in the plus or minus 5% tolerance. So we have this preferred resistor values for the E24 series. We're looking for 4.6. Now, the way these are done, right, if you look at it, 1R2 means 1.2 ohms. Yeah, the R replaces the decimal point. 12R means 12 ohms. 120R means 120 ohms. 1K2 means 1.2 kilo ohms, and so on. Yeah, we want 4.6. The nearest we got was slightly bigger, is 4.7. So trying to make this as real as possible, in real life, we'd have to pick a 4.7 ohm resistor for that series resistor. Yep.
Yeah.
So going back to our previous page, when we simulate this circuit, R1 is going to be 4.7 ohms because we can't get a 4.6, but we can buy a 4.7.
And you never want to go below it, right?